All the people who watch afterwards are going to be much less okay with it, but that's their fault.
So if all the audience can put themselves onto mute and maybe put their cameras off, then we'll let Sami start. He's going to tell us about the research done in the solar department at the MPS. Off you go, Sami.
Yes, well, first of all, thank you very much to have me give this talk, and particularly Sandra, who joined not my department, but the Institute some months ago. And she said it might be a good idea for me to just tell what we do here, because it's mainly solar. So you see most of the department members in this picture on the right, which obviously, as you can also see, was taken during pandemic times. Otherwise, we would have taken a group picture of everyone standing together. So MPS is shorthand for Max Planck Institute for Solar System Research, and we're in Göttingen in Germany. And next time there's a BCool meeting in this region, it might actually take place here. Okay, so I thought a little bit what to tell, because the department is, around 100 people, of which about 60 are scientists, including PhD students, and the rest is mainly engineers and technicians. And I thought I'll talk about tools rather than results, because the tools could be something interesting also for people who are doing stellar research, in particular stellar magnetism, because what we do mainly is solar physics. So we have tools, and this is a very incomplete list. There are many more that have been developed, and I realize that's something that it seems we like to do. Develop things that can be used to get results, and which have been sometimes used for many, many years, and improved as time goes on. So you can roughly put the tools into 3 different categories. One is modeling and simulation tools. Second category is data analysis tools. And the third one is instrumentation. I will talk about instrumentation very little, although it takes up a very fair fraction of the resources in the department, because that is really purely solar. If there is time at the end and Moira is gentle with me, then I might have a slide on solar orbiter, but otherwise we'll skip that. So I'll stick with the others. And again, I won't talk about all these tools, just about a few of them. And so I'll start with theory tools, MURAM, which is a radiation image decode. And it's been hugely successful. I mean, it's mainly been used to do solar physics. There are just a small handful of papers on stellar results as yet, but I think that'll change. That is changing, and it will change in the coming years. Just a sign of that it has been successful, the original description paper of the code, Vögler et al. 2005, has been cited 660 times by now, which for a solar physics paper, a theory paper, is a huge number indeed. So it's been, as I said, applied mainly to the sun, and it has successfully simulated a huge range of various solar phenomena, including, the quiet suns, granulation, larger features, convective features like supergranulation, solar and stellar faculae, sun and star spots, the small-scale dynamos, coronal heating, flares, loops, etc., etc. It goes on and on. What you see in the movies running on the right are 2 different sets of simulations. At the top, facular region or plage region, starting with an initial vertical field of 200 Gauss. And on the left, you see the vertical magnetic field. This is a box which is about 6,000 by 6,000 by around 3,000 kilometers deep. You see individual granules. On the right, you have the brightness. On the left, the field strength is blue, means very weak, till red means around 2,000, 2,500 Gauss. So you very quickly get these concentrated small-scale magnetic features at the intersections or at the boundaries of granules. On the bottom right, just for comparison, is a almost field-free, that means very quiet sun simulation with starting with an average field of 10 Gauss. And if you look carefully, you see that the granules are actually quite different in the two. So convection is affected quite strongly with that. It's just an example. The code has very low diffusivity, is very fast, and has a rather comprehensive physics needed to treat not just the solar surface and interior, but also basically all layers of the atmosphere. And we have a new version now that also includes the physics needed to treat the very, very tricky chromosphere. Here are some of the people who have been involved. Manfred Schüssler, who's now retired on the left, he was the brains behind it in the very early days. Robert Cameron and Matthias Rempel, who did his PhD here, was a postdoc here, but is now at HAO, developed it further. And Damian Przybylski, who is a postdoc, he has done all the hard work of introducing 1-LTE radiative transfer, etc. Now, why should one use this code? And one of the reasons is that it provides really excellent agreement with observations, and not just with convection, which there are a number of codes which do that really well, but also with magnetic features, which are harder to treat. And so just as an example, to give you a flavor of this, is an image produced by Matthias Rempel, where on one side, they're both, of a sunspot. Then there are two images there actually, and on one side is a simulated sunspot, on the other side is an observed sunspot. And the question is which, right? At this resolution, you really can't see much of a difference, but let's zoom in to a small part here, especially in the penumbra, which is the toughest part to resolve observationally and to simulate. And if you blow it up, then you can start to see some differences, and you realize that the one on the left is the simulation because it shows more fine scale structure. You don't have the resolution in the observations to resolve all the finest scales, which you have in the simulations. So, but it's doing remarkably good, and not just at this level, but also if you compute spectra, etc., etc. And so one of the things we have started to do is to also simulate stellar features, star spots. There will be a talk later today by Mayuk Panja, where he will show you such simulations of star spots. And here you have 3 of them, but maybe I shouldn't just say anything. Let Mayuk do the talking also. Also, Tanavir Bhatia, who is, Mayuk just finished his PhD a few months ago. Tanavir is working on his PhD, and Tanavir will be telling you about small scale dynamos and how they influence convection, etc., on different stars along the main sequence as well, just like Mayuk has been doing. Then another code, which was the developments were started at NPS, and Robert Cameron has been working on that a lot. And Emre, Emre Ishik, who has left and is now back in Turkey, is a code which actually combines 2 different things. And actually Manfred should be there as well. He was our big theory guru before he retired. So flux emergence and transport, this is a combination of 2 different codes. And what you're seeing in the movie running here is the flux transport bit, where you emerge bipoles at the surface of the sun, or it could, in this case, the sun, but it could also be stars. And then you let the field evolve with time. It's just one of multiple such codes around. The emergence part includes something else of what is going on below the surface. So if you have a dynamo located in the lower part or at the bottom of the convection zone, then your magnetic flux from there has to reach up to the surface. And the dynamics of how this happens is something which is also taken care of in this combined code here. And so by combining that, you can determine a little bit with still quite a bit of uncertainty. You could combine it also with the dynamo code, which is possible, but there are still lots of uncertainties there, what's happening with the dynamo actually in different stars. So you can also just parameterize things and try out different stuff and know that the physics you're using for the rest of it is maybe a little bit better. So what this set of codes does is provide you the distribution of the magnetic flux and its evolution at the surface of a star. In contrast to MURAM, which provides you the details of the structure and dynamics of individual magnetic features or groups of magnetic features on the stellar surface. Okay. And of course, both from MURAM and from FEAT, you can then be combined, as I said, with dynamo models, but you can also extrapolate the magnetic field into the corona and even further out into the stellar wind if you want. Just a result from FEAT shown here is a simulation that was carried out by Emre and co-workers. This is of a G2 star, G2 5-star, so pretty much like the sun. And the only thing that was changed was the rotation rate, and the assumption was that the dynamo doesn't change. That means you, at least the latitudes at which your flux is produced or enhanced at the bottom of the convection zone doesn't change. The amount of flux obviously increases as you go from slow to fast rotation. And then you let these flux tubes that are produced at the bottom of the convection zone rise through the convection zone, being affected by, among other things, the Coriolis force. And then you let the field evolve at the surface. And you find that whereas for a star rotating at solar rates, you have most of your field concentrated all the time at the at lower latitudes, except at the minima where you get something at the poles. These are just snapshots in the lower right image. Whereas if you go to a very rapidly rotating star, which is at the bottom right, you start getting something like a polar spot, where because it's a G2 5-star on the main sequence, the convection zone is not very deep, so you would not actually get a polar spot or such a high latitude polar ring just from the emergence of the field, but combining the emergence with the surface flux transport produces that. So let me move on very quickly. Let's come to Satire, which is another code or set of codes actually. And Satire stands for Spectral and Total Irradiance Reconstruction. And it takes your surface distribution of magnetic fields, which you could get from FEAT, or you can get it directly from magnetograms if you're working on the sun, and that's what we were doing. Plus, if you know something about the structure, the atmospheric structure, which you can get from 1D models, which were produced by Yvonne Unruh, for example, which you did for a long time, or you can take them now, what we are doing directly from MURAM simulations. So you need sunspots, you need Faculae network, and you need quiet sun. And with these three components, as we call them, and their respective model atmospheres, we can go ahead and compute the variability of the sun, for example, of the total irradiance. That means the total brightness of the sun as seen at 1 AU. Here again, the people involved, Marcel Flicke, who was a student of mine a long time ago when I was a postdoc at ETH in Zurich. He's now Director General of one of the major banks in Switzerland and probably earns more than all the participants of this conference taken together. And Natasha Krivova, who is here at the Institute, and Coquelin Yeo, who is also here at the Institute. And the figure at the left, you can see a comparison over roughly the last solar cycle, measurements of TSI by the TIM instrument on the source satellite, which are shown in red. And you can see there was a gap at a certain time. Where the source was not working. And the model is in black, which fills this gap because we had magnetograms for that time. And the long-term agreement is very nice. There are two blow-ups of the times on the left. this little box here, which is shown as the second image. And also there at shorter times, you see the agreement is really excellent. And we have shown that just the magnetic fields at the solar surface are responsible for more than 95% of the solar variability on a time scale of days to decades. We cannot really say longer than decades because that's the longest that we have observations for where we can test it. However, you can then take the model and go ahead and reconstruct irradiance also on much longer time scales and covering, for example, the entire Holocene, that means the last 10,000 years, which is quite important for solar input for climate studies, or at least starting from the Maunder minimum. And this is a recent result that Coquelin found, that if you go back to the Maunder minimum in the second half of the 17th century, when the sun was totally inactive, it was less than 2 watts per square meter darker than it is today. And that's little. There have been other models which have claimed up to 6 watts per square meter darker. And that would have been sizable and would have meant that the sun a variable sun had a huge impact on climate change in this period of time. Whereas the limit that we have been able to set suggests that yes, it could still have, and there is evidence that on historic and prehistoric times, the sun did affect the climate, but the last bit of global warming that we have been having is very likely the sun has played a very minor part. You can also combine Satyr and Muram, which we have been doing now also, to determine sources of irradiance variations, not just limited to timescales longer than days. And this is something that Sasha Shapiro, who, by the way, plays a big role in applications of our solar codes and has also been developing his own tools with his group to cool stars. So he's leading an ERC starting ground group to apply to cool stars. Right now he's busy writing a proposal, which is why he cannot or hasn't been very active at this conference. So one of the things Sasha did a few years back was to use Satyr for a day or longer, use Muram for timescales of shorter than a day, which is mainly then convection, and show that together they reproduce variations or the power spectrum. This is the wavelet power spectrum plotted here over 6 orders of magnitude in power, and 8 orders, or also 6 orders or more, actually 7, 8 orders of magnitude in frequency or time, and reproduces it well. Yep, thank you. So basically it just says you only need fields at the surface and granulation to get almost all of that correct. What's missing in the model is the P modes, but they only affect a very, very narrow part of the spectrum. You can also use, from this we got the idea also, how to determine rotation periods of stars. And this is something that Eliana Amazo Gomez has, who's just finished her PhD also this year, played a prominent role. Determine rotation periods of stars like the sun, slowly rotating stars, where if you look carefully, the rotation period of the sun is plotted here, but there is no real peak, right? If we didn't know it was this little thing, it might have been this one, or something back here. It's really hard to tell. However, there is something else, right? When you have sunspots crossing the disk, they produce a dip, and the width of this dip, in this case of the transit, is around 5 days. And that corresponds roughly to the time where you have the strongest gradient over here. And you can make use of that to determine the rotation rate. They go along very fast here. Something else, another application of Satyr combined now with non-LTE radiative transfer in 1D atmospheres here. And this is work done by Soumya Krishnamurthy, Veronika Witzke, who will be one of the speakers later, and Sasha Shapiro, among others, is to compute the S index, right? The H and K lines of calcium, which you can see in the topmost plot over here, the two very strong lines, their cores, the amount of emission in their cores depends on activity. And we said, okay, can we understand that for the sun? And indeed, in black is 81-day smooth observations from National Solar Observatory of the calcium index, which has now been converted to the S index, and in sort of yellow-orange plotted over on top of that is what we have computed, again on a daily basis, but now 81 days smooth. And the agreement is remarkably good in this case. So once you have a model like that, you can then see, well, what happens if we look at the sun from different angles, because that is what is happening with stars, right? In the sun itself, we're always looking from the equator. And now we have the chance of looking at it from different angles. And not just that, because with Satire, we have the possibility to reconstruct the irradiance going back in time. And irradiance also means spectral irradiance. So you can reconstruct the spectrum going back in time of the sun, modulated by its activity. And you see that in the bottom plot. And on the right is what the sun's variability looks like as an inclination of 90 degrees, that is from the ecliptic, but also if you were directly over the poles, and they do look not entirely different, but they do look different. And then you can take this and compare what the solar variability could have been, right? And plotted here, this is from a paper by Rich Raddick et al., I think, or Lockwood et al., I don't remember, where you have now not the S index, but corrected for B minus V, the RHK. And here is the sigma, that is the variability on the y-axis. And you see there's a fair amount of scatter of stars, including stars like the sun. But we think that this could very likely, most of the scatter is due to the fact that we are seeing these stars from different rotation, different directions relative to the rotation axis, but also at different levels of activity and weak cycles, strong cycles. And if you do that for the sun, you get this red streak over here, and you see that just the sun over the last 300 years basically covers most of the variation that you see in the stars. There's maybe also some differences and maybe some noise. That means the sun has a very normal level of calcium H and K variability. I'll skip over the solar orbiter and just point out that there are more interesting talks to come by various young people at the Institute who are doing the real work. And I hope I have just given you a bit of taste for that. Thank you for your attention.
It's always very strange with these talks that you don't actually get the whole audience clapping. We have time.
Some of them are showing it.
Yes, they are. Yes, it's great to see that. Thank you, Sami. That was a great talk. Have we got any quick questions for Sami? Oh, no, you can hear my timer going off there. I have one while everybody's gathering their thoughts. When you talked about extending satire into the stellar domain, do you think you need to change not just the surface coverage of the individual elements, the spots and faculae and so on, or do you need to change their structure as well?
I don't know. So that, I mean, the way we would introduce, or we have been introducing satire to, and so far we have been careful to stay, you know, stars that are similar to the sun, maybe different rotation rates, but not different spectral types. That will be the next step that especially Sasha is contemplating of doing. And there you run into a hornet's nest because there are lots of things you don't really know. So we assume that you still have something like a log normal a power law distribution of bipoles which are emerging at the surface. So we go for the solar paradigm, right? And until proved wrong, that means if it doesn't agree with the data, we say, okay, we just start with the solar paradigm, and then we see where things come unstuck. But even with the solar paradigm, if you start introducing a lot of flux, you start seeing new effects. And this was something that turned up in Emre's paper of 2018, in which when you went to the really rapid rotator, you found, and we did a very, very simple thing. We said there is a threshold when the flux concentrations, the field strength goes above a certain threshold, then it's a spot. And we found that in addition to spots forming as they do on the sun, which is always by emergence, for a very rapid rotator, you also get stops forming by flux being pushed together, which happens at high latitudes. And if enough flux comes there, you could actually start producing polar spots as well. At least that's what we got from this threshold. So yes, you do get new things, but you say, okay, the underlying physics is the same, and then let's see what happens, and if it agrees with the observations or not.
Well, I look forward to seeing some of that stuff emerging. I think we have to move on.